Hello students. So today we'll discuss the probability distributions. So probability distributions, we have three types of distributions with us. The one we have binomial distribution, then we have Poisson distribution, and then we have normal distribution. So basically the distribution means when we are repeating the event multiple times, it is called as the distribution. For example, we have done one particular case, like we have thrown the dice or we have thrown a coin 3 times. Now I want to find what is the probability of one head in the 3 times of a tossing of a coin. So what we are doing in this case is we make all the cases of the 3 tosses of a coin, which is like head, tail, tail, head, tail, head, 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 tail, and head, head, head. And then tail, head, tail, 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 head, tail, head, tail, and tail, head, head. So all these are the 8 cases which can be possible for the 3 coins, and now I want to find for one head. So I can simply count the number of the outcomes in which we have only one head, which is 1, then we have 2, and then we have 3. So the probability becomes 3 by 8. But now this is only possible when we have a 3 times tossing of a coin. But let's suppose we have thrown this particular coin 6 times now. So now if this is a 6 times, I want to calculate for the probability of 2 heads from the 6 heads. So I want to have a probability of 2 heads from the 6 tossing of a coin. Now it is not, this is possible by making these all the outcomes for the 6 tossing of a coin, which will be 2 raised to the power 6, which is 64 cases. And which is not possible for us to make all those 64 cases, as we have easily made for 8, but not for the 6 times. That the 64 cases is not possible. So there the work of binomial theorem will come into play. So the binomial theorem says when we are repeating the number of event more than once, so in that particular case we can use the binomial distribution. So let's take this particular example only. I have tossed a coin 6 times, and I want to find the probability of 2 heads from 6. So that will be my question. So how we can do that? We can apply the binomial theorem to this. So binomial theorem says the first condition to binomial is that there must be only 2 outcomes of a single event. 2 outcomes of a single event. So single event here is we are tossing a coin. That is my event. So I am repeating that particular event number of times. So a particular event like a tossing of a coin has only 2 outcomes, head and tail. So then we can apply the binomial, as the word itself says binomial. So bi stands for 2. So that is why we can only apply the binomial theorem where we have only 2 outcomes of a single event which we are repeating number of times. So that is the first condition of the binomial theorem. So now here we want to calculate for like the 2 heads. So the condition is we want to find the probability of 2 heads. So the formula for binomial is NPR. We want to find the probability of 2 heads, which will be equal to NCR, P raised to the power R, and Q raised to the power N minus R, where N is your total number of trials, then R is the number of favorable events you want. Number of favorable event you want, like favorable outcome you can say, prove to be more precise. So here we want heads. So here it is 2 heads for our example. Then the P is probability of that outcome, favorable outcome, in single event. That is called as your P, and Q is 1 minus P. So this is the formula for the binomial, and we can apply here to get our result is N is in our example N is 6, then C 2, because we want to find for 2 heads. Probability P, small p is the number of favorable, probability of the favorable outcome, which is head. So 1 by 2 is the probability of a head in single outcome. So 1 by 2. Now number of R is the number of heads. R is your number of heads. So that is 2, and Q is 1 minus P, that is again 1 minus 2, which is n minus R raised to the power 4. So this is the answer we can solve to get our answer of 2 heads from the 6 total of the 6 tossing of a coin. So if you try the same case over here, so this can be written as in the form of probability we want to find for 1 head. So out of 3, so that is 3C1, 1 by 2 probability of head is 1 by 2 raised to the power 1, and probability of 1 minus P raised to the power 2. So if you solve this, so this will become 3, 3C1 is 3 into 1 by 2 into 1 by 4. So that becomes again 3 by 8, which match our logical answer. It matches with our logical answer, but it is only possible when we can do this on like 3 coin. The logic can be applied only when there is a 3-time tossing of a coin. But if I have tossed the coin 6 times, it is not possible to make all those 64 cases. So there is none other option but to apply the binomial to find my answer of like the same which we can apply through binomial distribution. So let's take another example. So let's suppose we want, we take the condition like we have a dice now. Now a winning situation is getting 1 or 6. So that is the winning condition, and losing is my 2, 3, 4 and 5. So this is my losing. So if I get 2, 3, 4, 5, it is a losing, and if I get 1 or 6 in the dice, it is a winning situation for us. So now I want to find that I have tossed the dice again 5 times. I have tossed the dice 5 times. I want to have that out of 5 times I have at least 2 wins. I want to find the probability of at least 2 wins from the 5 throws of a dice. So that is the another example we can take off. So here the probability of win. So here we are, n is 5 over here. R is we want at least 2. So at least 2 means 2 wins, 3 wins, 4 wins and 5 wins. So that is the case of at least 2 wins, because we can have a minimum of 2 wins. So that means 2, 3, 4 and 5. So either of these can be my answers. So for first case we have to find for 2 wins. So R is 2 win. Then your probability P is the probability of win. So probability of win is the 2 divided by 6 is the probability of win, and Q becomes 1 minus 2 by 6, which is 4 by 6. Fine. So I will apply the formula for 2 first is, so 5C2. So for P2 NCR, so 5C2, then probability is 2 by 6, which is 1 by 3 and raised to the power number of wins. So 1 by 3 raised to the power 2 and 2 by 3 raised to the power 3. So if we'll solve this, so 5C2 is 5 factorial divided by 2 factorial into 3 factorial divided by 1 by 9 into 8 by 27. So that will be like 5 into 4 into 3 factorial divided by 2 factorial, 2 into 1 into 3 factorial. So this is cancelled to 2, and then whatever the answer, that will be your probability of 2 wins. Then in the same case we can calculate for 3. So 3 wins is your 5C3, 1 by 3 raised to the power 3, 2 by 3 raised to the power 2. So we can solve this now. And similarly we can find for 4, we can find for 5, and then we can add all the answers, because it is like at least 2 wins, either 2, 3, 4 or 5. So we can add all these to get our required answer for the probability of at least 2 wins out of the 5 throws of the dice. So that is your binomial distribution. Now next comes the Poisson distribution. So Poisson distribution is theoretically same as that of a binomial theorem. So where we can apply the binomial, there we can also apply the Poisson, but the problem is, like we will see the difference now. Let's take this particular example of the dice. Here instead of tossing of a dice 6 times, So here we have tossed the dice 5 times, but instead of tossing of a dice 5 times, we have tossed it 100 times. So we have tossed the dice 100 times. So it will be now, if you apply the binomial, the same case to binomial for 2 wins. So the formula becomes 100C2. The formula becomes 100C2, and again the probability of is 2 by 6, or which you can say 1 by 3 raised to the power 2 and 2 by 3 raised to the power 998. So now this becomes the binomial theorem for this particular case. And now if you see this, it is very difficult to calculate the 2 by 3 raised to the power 998. Again, it will be very difficult to find 100C2 value, because 100C2 is 100 into 99 by 2 into 1. So the calculation becomes tougher, but still you can calculate this, but it is very difficult to calculate, or you can say infeasible to calculate 2 by 3 raised to the power 998, because you have to multiply 2 by 3 998 times. So that becomes the challenging in the case of the binomial distribution to apply. So here the role of Poisson comes. So the same question we can do it with binomial also, we can do it with Poisson, but still if there is, you feel like it will be a difficult to calculate these, so we can use with the help of the Poisson distribution. So there the role of Poisson will come, and the condition of Poisson distribution is, so thereby the role of the Poisson distribution comes. So Poisson distribution says when my n is very large and p is small. So let's take the example for this. So let's suppose a factory is there which is producing the output, and among the output, so let's suppose there is a consignment of a factory, and the consignment produces 1000 products, and it was found that from the 1000 products the probability of defective product is only 0.001. So the probability of defective product is only 0.001, and there will be a total product produced by the factory is 1000. And now I want to find the probability that out of these 1000 products, 5 products are defective. I want to find the probability of 5 products are defective. So this is the question for me. So now if I apply the binomial again to this, so this becomes like 1000 C5. What is the probability of defective is 0.001 raised to the power 5 and 0.999 raised to the power 995. So here this is again impossible to calculate, this is also like very impossible to calculate, so all these calculations becomes tough. So for that we can apply the Poisson distribution, where PR under Poisson, the formula for Poisson distribution is e raised to the power minus m into m raised to the power r divided by r factorial. So this is the formula you have to remember, where Poisson distribution is e raised to the power minus m into m raised to the power r divided by r factorial, where m is equal to n into p. So what we have done in the Poisson distribution, so n is very large, p is very small, so that will create a problem for me in binomial distribution, because n is creating a problem here and very small p is also creating a problem over here. So what we are doing here is we are multiplying a very big number with a very small number to get a medium number, and in the Poisson distribution we never use n and p individually. So we are using only the m in the formula, which is a moderate number, and we can calculate now very easily. So let's suppose in this particular question we want to calculate P5. So P5 is equal to e raised to the power. So first we'll calculate m. So 1000 into 0.001. So which is your 1. So answer becomes only 1 now. And in the formula we are using only m, not n and p individually in the Poisson. So that becomes e raised to the power minus 1, 1 raised to the power 5 and raised to the power 5 factorial. So that becomes the Poisson distribution answer. So now the challenge may be to find this e raised to the power minus 1. So you can have in the exam whatever the values of e raised to the power minus you have to use, so that may be mentioned in the question paper. So that is the solution for the Poisson distribution. But the condition is where my n is very large and p is very small. So there we have to do the question with the Poisson distribution. You cannot do that question with the binomial because it is impractical to do that question with the binomial, because these calculations becomes the tough. So the answer of this and answer of this is same, but because of the calculations issues, we have to use this particular formula Poisson for doing this type of a question. But where my n is large, where n is moderate and p is also like large enough, so we can make with the binomial distribution. So that is a difference between your normal and your Poisson and the binomial distribution. So in we are ending this. So in the next lecture I will be telling you about the normal distribution.